let me take a little bit of time and just review the few key points that we covered the last time. If you remember, we talked about random processes. And we discovered when you talk about random processes, you actually have two dimensions that you're concerned about. One is the amplitude dimension, saying what is the distribution of this process in the amplitude domain. And then when we characterize the process in the amplitude domain, what we usually give is PDF of the process. Let's say this is a random process x of t. So you're going to have PDF x of x, which will give us the distribution of the process in the amplitude domain. This is not the only way how you can specify it. You can specify it through CDF, you can specify it through moments. There are a couple of equivalent representations of the random process in the amplitude domain. But PDF is the most common, and it's self-sufficient. If I give you PDF, I've told you everything you need to know about the random process in the amplitude domain. Now, the second dimension that we're concerned about the random process is how does it evolve over time? And this is a time domain. And the way how we said we're going to characterize this random process is by giving the autocorrelation function in the time domain. Autocorrelation function that was defined R of t at a given time t. Actually, we can give this one also as a function of t, right? Because the PDF may change over time, right? How does the signal behave in the amplitude domain may change over time. The second descriptor is the autocorrelation function at the time t as a function of tau, and this was defined as expected value of x of t, x complex conjugate of t plus tau. And we said between these two, we have a full representation of the random process. We have its time amplitude characteristics and its time domain characteristics. What we did also last time, we defined something that we call stationary random process. So, stationary process essentially the process is stationary if it is stationary in the amplitude domain and in the time domain both, right? So if the process is stationary, if we have a first condition that is PDF x of t x is just a PDF x of x, meaning that for every t, you get the same distribution in the amplitude domain. It does not change over time. And then the second condition is that R of t tau is essentially just R of tau, where your autocorrelation function does not depend on t either, but just on a separation between the two samples in a time domain. So it's only dependent on tau, but not on t. So that's what we call stationary process. We had a weaker condition that we call widesense stationary. Here, we also have two conditions. One condition is this R of t tau is just R of tau, right? So autocorrelation function does not change. So the time domain characteristics is unchanged as a function of time. But here we have a weaker condition where we require that mu of t is just equal to mu and sigma squared of t is equal to just sigma squared. So we are requiring that the first two moments of the process do not change over time. Its mean does not change and its power does not change, but the rest of it may change, right? So this implies that all moments stay the same. Here we're just looking at the first two moments and saying first two moments are constant over time and the autocorrelation function is constant over time. If that's the case, then we call this process widesense stationary. Why is this an important category? Because a lot of our signal processing algorithms and a lot of our, I guess, analysis in general requires that the mean value of the signal and the power of the signal stays constant for us to do something, right? And we rarely pay much attention to the higher order moments. There are algorithms where this is also concerned, but in most of the algorithms that we deal with, especially when you talk about signal to noise ratios and those kind of things, then you really just talk about the powers, the ratios of the powers, and it's important to say powers do not change over time. Powers are stationary, and this is, as I said, weaker condition that's satisfied obviously more times than this stronger condition here. This is a very strong condition. You require that the entire PDF does not change over time. Nevertheless, some of the most important processes that we deal with are kind of stationary. Like if you look at, for example, noise, which is going to be a process of highest concern to us, it turns out that under some relatively nominal conditions, the noise can be treated as a stationary process. So that's the definition of the stationary. The second type of processes that we have to shed the light on are processes that we call ergodic processes. So let's define what ergodic means and kind of see how you divide all of these random processes into all of these different categories. So ergodic processes. Consider a random process x of t. That's our random process. And then we have a function g of x, which is a function of the random process. We can define two kinds of averaging in in general. This is like a general statement. And in other words, we can take this process and average it over time, or we can average across all the possible realizations of the process. First type of averaging, which is the one that we call ensemble averaging. What is ensemble averaging? Well, this is what we, I'm going to start here. I'm going to be looking at all possible realizations of the process. So let's say this here is the first realization of the process, but I'm not only looking at the process itself, I'm looking as a function of that process. So let's say g x1 of t, right? So I'm taking the first realization of the process, x1 of t, and I'm applying some function to it. In the most trivial scenario, g can be just mapping the process onto itself, right? G of x is equal to x. But it can be, for example, g of x can be x squared, in which case I'm looking for the power of the process. It can be absolute value of x, it can be sine of x, whatever that function may be. This is time. Now, I can look at the second realization, and this is now slightly different, g x2 of t, and so on. In general scenario, you have infinitely many of these realizations of the process. What are we talking about? Let's say the process is voice as a category of the random process. Then these x's are everything that everybody has ever said, right? All possible realizations of this process. And let's say g is, let's say, squaring of that process. So I'm looking at the power of across all of these possible realizations. If I specify a time, let's say this is the time t0, then I can define ensemble averaging as expected value of g of x of t equal to t0, right? I'm looking at what is the expected value of this random variable. I froze time t0. Every one of these samples here is a value of this function g of x at t equals t0. Obviously, if I look across all possible realizations, they form a certain PDF, and then I can take expected value as the expectations across these values that are forming this PDF. So this becomes integral when x goes from minus infinity to plus infinity, g of x times PDF of x when t is equal to t0 dx. Right? This is called ensemble average. If the process is stationary, then this t is irrelevant, right? This t0 is irrelevant, meaning that wherever on this t-axis, wherever I make a cut, I'm going to get the same PDF, therefore I'm going to get the same expected value, right? So for stationary processes, we can drop this at t equal to 0 and get the expected value of g of x is equal to integral when x goes from minus infinity to plus infinity, g of x times PDF x of x dx. Because PDF of x is now only function of x, not function of t, right? Because it's the same for every t. Now, what is the practical obstacle in using this kind of average? The fact that you need to have all possible realizations, which is practically impossible, right, because of this set is infinite. But even to get a good approximation, you need to have large numbers of them. Let's say I don't want to do all of them because I can't, but I do 1,000 or I do 2,000 or whatever needs to be the case to get enough sample large enough so that you get convergence in the statistical sense, right? Now, and a lot of times you actually have no choice. This is how you need to do it, and you just figure out a way how to accomplish the task. However, there is a class of processes for which we have an easier way out. So let me talk about time domain average. Time domain average. If I have, let's say, the starting point is the same. I have my realization x1 of t, and this is a g x1 of t. So one realization of this random process. Then I can define a time domain average, g of x, as a limit when t goes to infinity, 1 over t, integral over t, g of x, actually no need for 1, just g of x of t. Okay? This is something that is a good friend of ours. This is what we encountered before, right? This whole operator limit, 1 over t, integral over t, we know that this represents the time domain averaging. We used it before to define the power of the signal when signal x of t was a deterministic signal. Now here, the x of t is not a deterministic signal, it's a random process, or more precisely, it is a sample realization of the random process. Now in general case, if you do averaging this way, and you do averaging this way, you're going to get different results. Right? There's nothing that says that these two need to be the same. However, in some special cases, so in general case, expected value of g of x is different than this value. Right? There's nothing that says that if I average across all possible realizations, it is the same as the averaging over time. However, in a special case, these two may be the same. When that's the case, the signal or the process is called ergodic. Okay. Now the question is, okay, all of this seems quite abstract, but let me, before I go and give you some examples of when the process is ergodic, let me clarify the benefit of this. If the process is ergodic, what that means is I don't need multiple realizations of the process. I need a single realization of the process from which I can determine all the possible averages that I need. So let's say this g of x is just x. By doing this, I'm determining the average value of the process. If g of x is equal to x squared, then I'm determining the power. G of x equal x cubed, I'm determining the third moment, and so on. So I can assemble my entire PDF just by looking at a single realization of this process. From the practical standpoint, this is of a great value to us, because all I need to have is long enough realization of this process to be able to statistically describe this process completely. Let me spend a couple of minutes. I didn't put that in the notes, but I'll just give you an example of first the process that is not ergodic, so that you understand intuitively what that means. And then I'll give you an example of an ergodic process, so that you see why these two averaging essentially give you the same result. So, example one. This is non-ergodic process. Let's say we're having a group of students that are working on an electronics lab, right? An electronics lab, and they all have their power supplies. And let's say they all leave room forgetting to turn off their power supplies, right? And what happens in that case, if I now look at all the workstations, and let's assume for a moment that somewhat unrealistically that there are infinitely many students, right? So just not bounding the count this way. First student left voltage at this point, right? The second student left voltage at that point. The third student left voltage at this point. So this is, let's say, V1 of t, V2 of t, Vn of t, and so on, right? You can see that the voltage that is left on a power supply is going to be a random variable. It's going to take some value between, let's say, minus 12 and 12, because that's a typical voltage for a power supply. Now, that random variable is going to be different on any one of these generators, these power supplies. If I fix time, first of all, is this process stationary? Does it change over time? No. If I fix time at any place, I'm going to get the same statistics across all of these amplitudes, right? Now, if I look at this time, t equal t0, what is the expected value of v? What is the expected value across? What is the average value across all of these?
0.
0, right? So I expect to see 0, on average. Some people are going to leave it positive, some are going to leave it negative, some are going to actually make it close to 0, or whatever it is that they left when they leave the room, right? Now, that's the average across all samples, right? Now, let's take a look at average across every one of the samples. If I pick a random sample, you can see that the average here across the sample is going to be different than average across all the samples, right? So this is an example of non-ergodic process. If I pick one particular realization, the probability of having the same kind of average as across all possible realization is 0, right? You follow so far? This is averaging across the samples, an ensemble of realizations of this process. This would be averaging across the time, and they give me a different result. Let's look at an example 2, which is an example of average. Example 2. This is ergodic process. Consider a mind experiment where I have, let's say, many different resistors that are all having the same resistance value. Okay? They're all having the same resistance R. And what I do, I have a very sensitive voltmeter that I put here on the edges of all of these resistors. And I'm measuring the voltage that is happening across these resistors. Since the resistors are not at a zero temperature, there will be random motion of the electrons going through them. And as a result, at the ports here, there will be some difference in the potential. There will be some voltage. And that would look somewhat like this for the first resistor. So this would be V1 of T. It will look somewhat like this for the second resistor. And so on. Now, let's take a look at averaging in this case. If I freeze time, first of all, if the temperature doesn't change over time, that this process is obviously stationary, right? Because the statistics will not depend on any given time t0 that I choose, right? If I choose here and here and here, I'm going to get the same statistics across all possible magnitudes. But now let's say, what would be expected value of V of t if I do the averaging across all possible realizations? 0, right? There is no DC current, so the voltage has to be 0. If I pick one of these, what do I get? What do I get as an average? 0. So, and this would be true for every one of the moments. If I square all of them, and I take the average this way, and I take the average this way, I'm going to get the same result. If I cube them, if I take any moment, I'm going to get the same result. So this is an example of the ergodic process. Now, how do you intuitively see if the process is ergodic or not? What is kind of, this is not scientific, this is how I explained it to me myself when I studied this, and it kind of worked through my life. If you can take one of the realizations, and imagine I observe this V1 of t for a very long time, and then I take scissors and I start cutting pieces of it, right? And then I take these pieces and put them underneath. If that picture is indistinguishable from this one in a statistical sense, then I have an ergodic process. Strictly speaking, ergodic process kind of goes through all possible realizations of the process in a single one realization. If I monitor this V1 of t for a long time, it will actually get portions that look exactly like these portions that I'm lining up one underneath the other. So that kind of process is an ergodic process that you have, and for these kind of processes, averaging across the time and across the ensemble give you the same result. So we have kind of covered several types of processes so far. So let me draw a picture here. Say this is all random processes. Of all possible types, right? We have defined a class inside them that we call widesense stationary. How is widesense stationary class defined? You have a process for which first two moments in the amplitude domain don't change over time. The process has the same mean over time, the same power over time. An autocorrelation function does not change over time. If that's the case, the process is called widesense stationary. If you have a widesense stationary process, but you have not only that the first two moments don't change over time, but the entire PDF does not change over time, then you have what we call stationary process. Strictly stationary. and then subclass of the stationary processes for which I can obtain the averaging, either doing it in the ensemble domain or doing it in the time domain, are called ergodic. So these are my ergodic processes. Okay? Now, this scale here is arbitrary, but you can kind of, what is important here to realize the relationship. If the process is ergodic, it is automatically stationary, it's widesense stationary. But if the process is stationary, it doesn't have to be ergodic, or if the process is widesense stationary, it doesn't have to be ergodic, right? So kind of realize this relationship. What we're going to be dealing the most with are these processes. You know, because they're analytically the easiest one to deal with, and this is an introductory course. So we're really dealing with the concept. And it turns out, for what we are trying to do here, it's fun, right? Because most of the applications that we deal with are kind of falling with dealing with the processes that are falling within this category. Or if not within this category, then there's something special. They may have some other properties that we can explore. There's something called cyclostationary processes that are kind of encompassing this and so on, but we're not going to go into all of these details. So from now on, when I deal with the random processes, unless I specify explicitly, which I don't think I'm ever going to do, we're talking about stationary ergodic processes. And I'm not going to be repeating that. Maybe every now and then I'm going to say it. But what that means, I'm going to be freely taking the averaging either in ensemble domain or in the time domain, whichever one is more appropriate for a given situation, right?